Okay, in continuation of my earlier video, first video of the electrochemistry, chapter number 2 of class 12 chemistry, CBSE board. The chapter has been allotted 9 marks, the highest mark in the 10 chapters. So let's go to the topic. Let's try to understand what does the term conductance mean. The conductance denoted by G is reciprocal of resistance. For any metallic conductor, according to Ohm's law, resistance means what? It's the ratio between the potential difference applied across a conductor. Suppose this is a conductor, and what is the resistance of this conductor? It's nothing. It's simply the ratio of the potential difference that has been applied across the conductor to the current flowing through it, I, V by I. This ratio will remain same unless temperature and other parameters are kept constant. What does that mean? It means that, okay, that if this is V and this is the I flowing through it, the ratio V to I is R, right? So if the V changes, if you increase the V, accordingly I will also increase. The current flowing through will increase, but the ratio of V to I will remain constant, and that is called the resistance of the conductor. The resistance of a conductor is an intrinsic property. It will not change. Voltage increases, the current flowing through will increase, the ratio will be same. If you decrease the voltage, the current flowing through will decrease, and ratio will again be same. And that is called the resistance of the conductor. And the inverse of that resistance is known as conductance. Conductance, depending upon which kind of material it is, whether it is a metallic conductor or an ionic solution, that is what we are concerned about in electrochemistry. Where we are learning, will always be interacting with solutions, ionic solutions containing ions in it. So conductance of the electrical conductance, that is conductance of the metal, is inversely proportional to temperature, but it is directly proportional to temperature in case of ionic solutions. That means if the temperature increases, the conductance of that electrolytic solution or an ionic solution will increase. But on the other hand, for general metals, if temperature increases, the conductance will decrease. Now let's go to the next move on to the next topic. It's the measurement of kappa, that is called conductivity. The measurement of conductivity of ionic solution. How we define the conductivity? And for that, you need to know that suppose that conductor, the potential difference and all, if you keep the potential difference same, the current flowing through will be the same. But if you change the shape of the conductor, its length is L and its cross-section area is A. If the length the resistance of the conductor is proportional to its length, so it'll increase the length, the resistance will increase, and it is inversely proportional to the area of cross-section A. So when you combine those two equations and you change the proportional sign, you get a constant. This constant rho is known as resistance is proportional to its length. Resistance is directly proportional to the length and inversely proportional to the area of cross-section. And if you replace the proportional sign by equal to, you have to then insert a constant, and that is called the resistivity of the substance, which, if the temperature and other parameters are kept constant, is constant. The resistivity of the substance. We are not defining resistivity, and inverse of that resistivity is known as conductivity. So instead of writing resistivity, I'm writing 1 by conductivity, because resistivity is the inverse of conductivity, or conductivity is the inverse of resistivity. Fine. And the constant L by A. Suppose now what is a problem in measuring the resistivity of a conductor? By using Wheatstone bridge that you have learned in physics. Wheatstone bridge is an arrangement of 4 resistors like this: R1, R2, R3, R4, in which you know the resistance of 3 conductors. Okay, this may be like a variable resistance. Fine. R1, R2, R1, R3, and R4 are known. The resistance R2 is unknown, and we are going to find out the resistance of this resistor. But here in our case, it won't be resistor; it will be an ionic solution. And for ionic solution, we need to use this kind of apparatus that is called electrolytic conductivity. That is called conductivity cell. This is called conductivity cell. The solution, the ionic solution for which you wanted to measure the conductivity, it has to be put in conductivity cell. Okay. Then if you use a DC source, a direct current source, it will change the composition of, it may react, the electrolyte may react, chemical reaction may take place. So we use generally an AC power. And another problem is that we need to use a conductivity cell because it's not possible, because it's a liquid, it's not really possible to join these wires to the liquid. So we need to use a conductivity cell. Okay, fine. Now, in the conductivity cell, suppose this is the portion of the conductor of the ionic solution. Now it has been treated like a metallic conductor. It's shape of metallic conductor, where the wires are connected like this. There are 2 electrodes, mostly platinum electrodes. So that it doesn't, because platinum doesn't easily react with will not easily react. It's very stable. It's what inert. It will not easily react with the electrolyte. So we generally use platinum electrodes. And the length between these 2 electrodes will be this L, and the plate and area of the plate, that the platinum plate that you're using, it will be A. And this ratio L by A is denoted by G asterisk, which is called the cell constant of this conductivity cell. It will remain constant, right? No matter if you can change the liquid inside inside the conductivity cell for different ionic solution. We can change the ionic solution if we want to measure the conductivity of the ionic solution. The ionic solution will get changed. But the platinum rods that you're using here, the platinum plates that they're using there, its area will remain constant. Its length is constant, its area is constant. Then that L by A will remain constant, and this constant is called the cell constant of this particular conductivity cell. Now the problem is, first you need to know, okay, our target, our objective is what? It's finding the conductivity, right? And in order to know the conductivity, in order to know, according to this equation, okay, if kappa comes this side, then rk is equal to cell constant, right? So if you want to know the if you want to know the conductivity, you need to know the cell constant. You need to know cell constant and the resistance of the conductor. When you know the cell constant and the resistance of the conductor, you can calculate the conductivity of that ionic solution. True. Now, how will know the cell constant? It's very difficult to like break it, and so before make a cell constant of the reaction, I'm not going deep in it. So say there are first in order to know the cell constant of the conductivity cell, we use like some electrolytic some ionic solutions whose conductivity are already known. We know the conductivity, and we know its conductivity at different temperatures. For example, potassium chloride. We put the potassium chloride first, and we know its conductivity, and finding the resistance, we can know its cell constant. Once the cell constant is known, once we know the cell constant of that electrolytic conductivity cell, now you can put the solution, ionic solution, that for which you wanted to measure the conductivity. Fine. So you put it, and if you know that it's resistance, if you can calculate the R2, the resistance, and you know the cell constant, then you can measure the conductivity of the ionic solution by using this equation. Fine. And how does the Wheatstone bridge work? It's there in your physics textbook. The Wheatstone bridge, this particular arrangement in which there are 4 resistors, out of which 3 of you know the value. So you use in order to pass the electric current through it, you use an AC power, right? And this is a detector. When there is no current flow through the detector, it may be an headphone. That means the Wheatstone bridge has come by adjusting the resistance of this R1. There will be a point in which no current flows through this detector. In that condition, it means that there is this Wheatstone bridge has reached an equilibrium. At that particular moment, you are getting the R1, R3, R4. You already know the resistance. So by using this equation, that R1 by R2, R1 by R2, in that condition, when no current is passing through this detector, R1 by R2 is equal to R3 by R4. And this has been done according to the Ohm's law. And the what we call the way we find the equivalent resistance for when the resistors are connected in series or in parallel. Using that using that relationship, R1 by at that condition, R1 by R2 is equal to R3 by R4. So knowing the value of R1, R3, and R4, the R2 can be calculated. If you know the R2 means resistance of this conductivity cell, that or in other words, the resistance of that ionic solution that you're putting in. That means that means R2 means that means you know the resistance, and you already know the cell constant. Then conductivity of the cell can be calculated. This is how the conductivity of an ionic solution is measured using the Wheatstone bridge. Fine. And what is molar conductivity? Now, for particular ionic solution, as the temperature changes or as the concentration changes, its conductivity changes. But there should be some quantity. There should be some quantity. There should be some significant. There should be some property of the solution of the ionic solution which should not change. So that particular quantity is called molar conductivity. So what is molar conductivity? It's not simply on this conductivity. The molar conductivity will be equal to conductivity of that ionic solution when the distance between between the two plates, the platinum plate is 1 meter, and the area of cross section is 1 square meter, or say unit distance. When the distance between the two plates is unit distance, in the solution is unit distance, and the area of cross section is unit area. At that time, or the volume of the solution is unit, and the solution having molar conductivity of an ionic solution is defined as the volume of the solution containing 1 mole of solvent, 1 mole containing whose concentration is 1, having unique concentration. At that time, the conductivity of the solution is known as molar conductivity. Fine. Molar conductivity of a solution is the conductivity of the solution. Now, how has this come? Now look at this one. Here, as I have already told over here, the resistance of a conductor is equal to rho resistivity into L by A, which is not a cell constant. Resistance is what? It is inverse of conductance, and rho is what? It is the inverse. It is equal to inverse of conductivity. Now, if you reverse this, G is equal to Ka divided by L. It's keeping everything upside down, right? So G becomes equal to K by L by A. Now keeping this in mind, this G, the conductance, now this will be if the area of cross section is unit, and if the length if the length there is unit length, then this quantity will be written as conductance, will be written as molar conductivity. So molar conductivity of an ionic solution is nothing but the conductivity of the ionic solution between unit area and a distance having unit length. Maybe square meter. If it is in centimeter, then centimeter square, and distance is 1 centimeter. If it is in meters, the area cross section is 1 square meter, and the distance between the two platinum electrodes is 1 meter, having unit area with a unit length, or in the unit volume. So molar conductivity of an ionic solution is nothing but the conductivity of the ionic solution with a unit volume. Fine. What about limiting molar conductivity? We find that as the volume increases, right? If you increase the volume, if the volume keeps on increasing, the molar conductivity will increase. So at infinite volume, when the volume approaches infinite, at a large volume, that means volume increase means concentration becomes zero, and concentration is near zero. At that time, the conductivity of the solution will be highest, and that conductivity is known as limiting molar conductivity, and it's denoted by symbol this symbol, molar conductivity, with a knot above it as a subscript. It has a super subscript. So limiting molar conductivity is the conductivity of the solution when the volume approaches infinite volume, or concentration is highly diluted, or concentration is zero. It tends to zero. It approaches zero. Now next, there is one more important topic that I want to cover in this video. It's called Kohlraush law of independent migration of ions. It says that the limiting molar conductivity of any ionic solution is equal to sum of the limiting molar conductivity of the individual ions in it. So this is cation, and this is an anion. For example, for sodium chloride, suppose take sodium chloride as the ionic solution. Its limiting molar conductivity means conductivity at infinite dilution when concentration approaches zero, right? At that condition, the limiting molar conductivity of sodium chloride will be sum of the limiting molar conductivity of the sodium ions and the chloride ions. It contains 2 ions, sodium ions and chloride ion. So if you know the value of these two, when you add these two, you will get the limiting molar conductivity of its solution. What about this one? This is general form where V plus and V minus denotes the number of ions in its formula. V plus and V minus. This is the limiting molar conductivity of individual ion, and these are the number of cations or number of anions that are formed in the solution. And for weak electrolytes, I would just want to add one more thing: the degree of dissociation. How much is dissociation? How much when making a solution, when making an ionic solution, how much is it's not like all for weak electrolytes. It's not like all the ions are dissociated. Some are undissociated, and most of the ions are dissociated. So what is the degree of dissociation? It is the ratio of the molar conductivity to the molar conductivity to the limiting molar conductivity. The degree of dissociation is nothing but the ratio for weak electrolytes, where some part, not all the molecule, but some part of the some number of molecules will get dissociated. So how much has been dissociated? Say suppose there are 100 molecules. It's not that all the 100 molecules will get dissociated. Say, for example, 80 molecules will get dissociated and 20 remain. So what is the dissociation? 20 by 80, right? Or 20 by 100. So what is the degree of dissociation? It will be ratio of molar conductivity to limiting molar conductivity. That is conductivity at infinite dilution, or when the volume approaches infinity, or concentration approaches zero. This ratio, the ratio of these two molar conductivity and limiting molar conductivity, gives the degree of dissociation of weak electrolytes. Please remember this relationship. Okay. In the next video, I will try to finish this chapter in 3 videos. That will be the third part of this chapter. Bye. See you again.